All right, you guys can turn to page 26 in your packet. We're gonna finish up with particle motion, with this review. Then we'll start, chain rule. And tomorrow we'll do another review for, 2.2 and 2.3. Chain rule is not gonna be on the quiz, but I do wanna start going over that topic. But let's finish up on page 26 first. Talked about how we get to velocity and acceleration function easily just by taking the derivative twice, right? First derivative is always velocity if we're starting with position, and then your second derivative is your acceleration. A, B, and C were pretty straightforward. After we found the velocity and acceleration, we can evaluate the velocity at a specific time. So insert 2 in for t for the velocity function, and we will be able to get the velocity at that moment in time. Unit of measure for velocity is feet per second. It depends on whatever the problem says. Right? It could be meters per hour. It could be, kilometers, per minute. So really you have to read a problem to match the appropriate unit of measure. Acceleration is, in this case, feet per second, so feet per second squared. Finding average velocity. So this one is one that has given students trouble in the past because we see that word velocity and naturally we want to gravitate towards using velocity because why not? There's a velocity function, so use it for average velocity. But the definition for average velocity is change in position over change in time. So we don't use the velocity function. Instead, we just rely on the slope between two endpoints, right? So the change in position divided by the change in time. We do not touch the velocity function for average velocity. Okay, part E, when is a particle at rest? We have to interpret that correctly. A particle at rest is when the object is motionless, and the object is motionless when velocity is 0. So we take our velocity function, we set it equal to 0, we factor, try to solve for t, and we get 1 and 5. Okay, next up, when is a particle moving right? When is a particle changing direction? So in order to do this, we need to create a sign line, but on the quiz, I'm not going to say create a sign line. You're going to have to make that connection where you have to understand that your sign line is going to help you gather all that information. So we start off by taking our values where our time shows velocity 0. So we place 1 and 5 onto our sign line. We also include 0 because they do give us a restriction. So we're starting at 0 and we're moving to the right because there's no value less than 0 for this problem. And then we choose test points. So I chose 1/2, 2, and 6. You can choose any value as long as they fall within those intervals. And we insert into what to test? Velocity. Yeah, into a velocity function, right? Because we're looking for the specific velocity value. So 1/2 into the velocity. Typically, we like to put it into the factor form because it's a quick way of getting whether it's positive or negative. So 1/2 gives me negative times negative, which is positive. So I know that in this entire interval, my object is moving to the right. Insert 2 into the velocity, I get negative. Insert 6 into the velocity, I get positive. So moves right, stops. Turns around, moves left, stops, turns around, moves right. From here, you want to go ahead and cross out your test points because they're no longer going to be used for anything that comes after. Okay, we don't want to accidentally use 1/2, 2, and 6 when we are creating these intervals of increased direction. So we're just relying on 0, 1, 5, and infinity and the signs, but we don't want to use those numbers ever again. Okay, when is a particle moving to the right? Moves to the right whenever positive is exhibited. So we know we'll go from 0 to 1 and then also from 5 to infinity. Most of your intervals will always be parentheses, except for a situation where the particle could be moving already. So here we need to test zero because zero is not a place where this object is stopping, right? It's only stopping on 1 in 5 seconds. At zero, it seems like it's already moving. But we need to test zero because it's part of our domain. So if I insert zero into the velocity function, I'm going to get a positive value. So this object's already moving at t equals 0. It's just that, the timer didn't start until after it started moving. So t equals 0, it's already moving. So we need to include bracket for that. And then next, we need to say, give justification. And the reason is because our velocity is greater than 0. Okay, next up, when does a particle change direction? So at what t values do particle change direction? What can we say? At t equals what?
1 in 5.
Yep, 1 in 5. The reason is because velocity changes signs. Part G, what is the displacement of the particle from 2 to 6 seconds? So displacement is just final position minus initial position. It kind of looks like average velocity, but then just without the time component. So it's just final position minus initial position. You can't get a negative value, which is fine. That just means that your progress is that you're making you end up 5 or 6 units or whatever the unit is behind where you or to the left of where you started. Insert 6 into the position function, insert 2 into the position function. So x of 6 is negative 25. X of 2 is negative 5. And on the quiz, I'll make these numbers easier to work with, so you're not spending half the time doing calculations without a calculator. But I want to make sure that we understand how we get these numbers, right? So 6 into the position, 2 into the position, and just subtract those. So negative 25 minus a negative 5. 2 negatives become a positive. We're left with negative 20 feet. So this tells us that this object is going to end up 20 feet to the left of where he started. 6 up if you compare the positions between 2 and 6 seconds. Okay, so that's not too bad, right? Displacement is not too bad. It's always final minus initial position. It's total distance that could require more work. So with total distance, you're going to start off with the same information as displacement. You're going to find the initial location. You're also going to find the final location. The question is, do we have to include any other locations in between the starting and end point? And this really depends on if there is a change in direction somewhere between the 2 time periods. But we're going to need something to help us out. Is there something that can help us out to see if there is a direction change? Velocity sign line, right? So we do require that velocity sign line to be in place already for us to get a good read on what's happening. If there was no direction change, then your answer will look exactly the same as your displacement, right? If you're just going the same direction that you were going without going back or changing direction, your displacement and distance will be the exact same value. But look at our velocity sign line. Is there a change in direction somewhere between 2 and 6 seconds?
Yeah.
There is, right? So we need to figure out the location at 5 because that is where this particle is going to turn around and start backtracking. Okay, so we insert 5 into the position function. It'll save us the work here, but that will end up giving us negative 32. Okay, so I think the easiest way to work through this is understanding from a visual perspective what's going on. So imagine you are along a number line and you're just taking steps to move from one location to the next, and you're just keeping a running total in your head. You're just every step you take, you're going to add that to your running total. So let's not worry about the time. The time is not that important. It's the location that's important. So it helps. Go ahead and put those onto a number line so you can kind of see where they are. So it has to be accurate, but just as long as, or to scale, as long as you kind of can have those numbers in order here. -32, -25, and then to the furthest right is -5. Okay, so you're starting at -5, okay, and you're walking towards -32, and then you're counting your steps. So how many steps would you have taken if you're on a number line and each step you progress towards -32? Right, and all you do is you just subtract those numbers and you're counting steps, so you want your number to be positive. So -32 minus -5 is -27, but you've taken 27 steps, so positive 27. And then you're turning around and you're walking from this point towards -25. How many steps would you have taken there? 7 steps, right? -32 minus -25, that's, you make it a negative number, but just keep reminding yourself, okay, I'm just walking along this path and I'm just counting my steps. So after everything is said and done, how many steps would you have taken? 34, and that is your total distance. 34 feet. Okay, so I see students tend to miss this problem as well, so any questions here? Okay, last two here. Is the speed increasing or decreasing at t equals 4? If we want to determine increasing and decreasing speed or decreasing speed, we have to do some comparison. Do you remember what we have to compare? Velocity versus acceleration, right? Velocity versus acceleration. So we're looking for what the signs are, right? So let's find the velocity at 4. Let's find the acceleration at 4 and see what information we get, okay? Really, the number is not that important. It's whether it's positive or negative, but let's go ahead and find those values. If I insert 4 to the velocity function, 3 times 4 squared minus 18 times 4 plus 15, okay, it's going to end up giving us a negative value, so -9%. Okay, acceleration at 4. 6 times 4 is 24 minus 18.
Negative value.
Well,
Oh, no, not 20.
positive, right? So 24 minus 18 is 6. Okay, so 6 feet per second squared. The importance is that one is negative and the other is positive, which means that speed is what? Say it again? Decreasing. Good. So if one is positive and the other is negative, if they have opposite signs, your speed is decreasing. If they're both the same signs, then it's increasing. So if these are both negative, it's increasing. If they're both positive, it's also increasing. So we can say speed is, in this case, decreasing. Speed is increasing because velocity and acceleration have opposite signs. Okay, part J is another one that students have some trouble with. Is velocity increasing or decreasing at t equals 2? Can I just look at the velocity and check the sign and just go from there? Okay. So this is not asking about velocity here. This is talking about what? About acceleration. Okay. And the reason I think students maybe have some trouble here is because some of us may interpret this as is velocity positive or negative, right? That sounds like the same thing as increasing or decreasing, but it's not. Here, if it's positive or negative, then we just look at the sign of velocity. But that's not what the problem is asking. It's asking for, is the velocity increasing or decreasing? And that is changing the unit that we're dealing with. We're not talking about velocity anymore. We're talking about the rate of change of velocity. We're really talking about just acceleration. So in other words, this is saying, is acceleration positive, which would be velocity increasing, or negative, acceleration negative would be velocity decreasing. So let's find the acceleration at 2 and make that determination that way. So, yeah. Yeah, we know it's acceleration because we see the word increase or decrease. Increase or decrease of velocity. So in other words, this is saying, what is the, it's talking about what's the rate of change of velocity doing? And acceleration is defined as the rate of change of velocity. So anytime we see that increase or decrease, understand that it's changing the unit or the value that this is referring to. Good. So you can understand why this gives students so much trouble, because the wording, you can be thrown off by the wording. Okay. So acceleration at 2. What's the acceleration at 2? -6. And we don't look at acceleration. We don't look at velocity. We just look at acceleration. So just from this alone, what can we conclude? Velocity is decreasing. Yeah. So we say velocity is decreasing at t equals 2 because acceleration is negative. Okay, so put a big star next to this. More than likely, you'll see this on the quiz. And there's always quite a few students who miss this problem. And with good reason, because it can be confusing, right? And then look at I and J, okay? Look how similar they're worded. That slight difference in wording changes the way we approach the problem, right? So pay attention to that as well. Okay, any questions? All right, let's look at, let's start our today's topic, which is chain rule. Okay, page 29. Okay, so chain rule is an important topic. It naturally progresses from product and quotient rule and chain rule. They all kind of have a similarity in the sense that they all talk about a relationship between two separate expressions or two different functions. So again, this is not going to be on the quiz, but we will see this as a big topic on the test. And also, we're going to see that chain rule is going to make product rule more useful as well. Right? There are most situations that we've seen so far really didn't need product rule because we had power rule to use because we could expand. But chain rule allows us to deal with problems that are more complicated. So chain rule is the method of computing derivatives of the composition of two or more functions. This is basically a function within a function. So let's review the different relationships so far. We've done product rule, which is the multiplication between two expressions. We've done quotient rule, which is the division between two expressions. And now we're talking about chain rule. This is a composition. This is a function within a function. So we have to be able to recognize that and be able to know when to use it. So here's the rule. The rule is, if I have a function within a function, such as this form of f of g of x, and we'll talk about what that would look like in the real problem, we're going to ask for the derivative of it. So that d over dx means the derivative of this function is going to be this rule. So what this rule says is take the outside function's derivative. You see that f prime, the f prime is outside the g of x. So this means take the derivative of the outer function. Multiplied by, okay, oh, and then when we take the derivative of the outer function, we're going to rewrite the inside function and leave everything alone, okay, because we're not ready for the inside function yet. Next up, times multiplied by the derivative of the inside function or the inner function. That's what that G prime is. Okay, so just to recap the steps, take the derivative of the outside function while keeping the inside portion unchanged. So that's what this is doing. Times, then multiply by the derivative of the inside term, which the original inside term is this g of x. So now we can let it take its derivative, and it's going to be in a separate space than the f prime of g of x. Okay, so let's look at example 1. Now, looking at this example here, let's say we only had the rules that we have learned up to this point. How would you go about finding the derivative if you were presented with this a day or two earlier?
Probably a really ugly FOIL.
Yeah, exactly, right. We can do it, right? But we're going to write out the parentheses 5 times. We're going to FOIL it out. I mean, there are methods using Pascal's triangle, but it's cumbersome. And that's not the point of this course. We're not doing a lot of messy calculations. So there is a way, but we want to have a more efficient way of dealing with a problem that has this much messiness, right? Because we don't want to deal with anything greater than the 2, especially if we're trying to just rely on power rule. Right? We can do power rule for a squared, but anything greater than 2, it just feels like it's too much work, or more work than what we would like to do. So what if we could think of this as 2 separate functions? Okay. So this is what we can do here. We can think of that there's an outer portion to this expression, and then there's an inner portion to this expression. If we can kind of split them up into 2 separate categories, then we can have a way of working through this using chain rule. So the outer function is basically the parentheses with anything that's outside the parentheses. So your outer expression is that parentheses to the 5th power. And then what do you think the inner function is? Yeah. What's inside the parentheses, right? So the parentheses will be very helpful. It's going to help guide what's outside and what's inside. Okay, so now that we have an outside and inside function, that tells us that we can use chain rule, because that's exactly what chain rule does. It allows for that outside and inside portion after we identify to be able to use it in that form. So we're going to pretend like the parentheses is its own variable. Okay, so pretend like it's an x. So let me just ask you this: what's the derivative of x to the 5th? 5x to the 4th. Okay, so now replace the x with the parentheses. If I ask you what is the derivative of parentheses to the 5th power, you would say 5 parentheses 4 to the 4th. So that is going to represent this f prime that's going on. We're taking the derivative of that outside portion. Okay, so we'll follow the rule here. What goes inside the parentheses? The original expression. Okay, so that's important. We're not doing the derivative yet. Derivative comes later, right? It's the original inside function. So it's important that we not only follow the rule, but then we were able to use the rule. Okay, times. Okay. Now we can do what? G prime, which is 6x. Much more efficient than having to FOIL everything out, combine like terms, do power rule for all the terms there, and then combine and factor it again and get it down to cleaned up, right? We're able to get to that point. Something that will take 10 minutes, we can scale it down to less than a minute. Okay, so here's the derivative. It's almost there. I mean, we basically have the derivative. I can just do a little bit of cleanup. I can push the 5 and 6x together. So there's our derivative. So I want to keep reminding us that as complex as our derivative process is going to get, ultimately, it still does the same thing as other derivatives, right? All it does is it tells us the slope of the original function, right? That's a simple concept, but we're just exploring all the different possibilities of building derivatives for different types of different functions. So whatever this graph looks like, you can insert an x value into the derivative, get a number, and that number will correspond to how steep this point is on the original graph. Okay. Before we touch about example 2, there's something small I want to bring up because this I skipped over from the 2.1 notes. I forgot to go over this, but it's not a big deal. It's just I just want to kind of go through the definition. This is in the 2.1 packet. You guys don't have to bring it out. I just want to go over this definition here. This definition is about differentiability. So differentiability tells us that it basically just means that can I find the slope at a point? So in other words, differentiability just means, is it a smooth curve? Because if it's a smooth curve, then I'm able to find the derivative at any point. I can find the slope at any point if it's along a smooth curve. The issue is if there's any sharp turn that shows up, then I'm not able to draw a tangent line to that point, right? You can't draw a tangent line because the slope doesn't exist. So here we say that this function is not differentiable because I'm not able to find the slope at a point. So differentiability just means that you're able to find the slope. It's a smooth curve. So if there's a sharp turn, not differentiable. Also, if there's a vertical tangent where the tangent line to the curve is a vertical line doesn't have slope. So this is also a place where the slope is undefined. So these are what graphs could look like if it's continuous, but not differentiable. So basically just any sharp turn, any cusp, anything that looks like where there's a corner, right? If you can identify any corners of your graph, you're going to have a place where the slope is undefined. We cannot create a tangent line to that point. Okay. Oh, this is on the 2.1 packet, which I gave you, and we already went past it, but it's in the 2.1 differentiable derivative tangent line problem. But I just skipped over the notes there on the second page with differentiability. Okay, so example 2. Find all the values of f of x for which f prime is equal to 0 and where f prime does not exist. Okay. So there's 2 things that I want us to be able to write down before we go through our process of derivative. Is this. Okay. So to find where f prime is equal to 0, what does that mean? F prime is equal to 0. That means what?
You have to set it equal to 0.
Describe it in a visual sense. What does this mean? F prime equal to 0.
Slope is
Slope is 0, right? Slope is equal to 0. So to find where slope is equal to 0, the steps you're going to take is you're going to set the numerator of the derivative equal to 0. Now, if there was no denominator, sorry, if there was only a numerator and no denominator, then it's the entire derivative equal to 0, right? But if there was a numerator and denominator, then setting the numerator equal to 0 versus the denominator equal to 0 is going to produce different results. So if there's a numerator versus denominator, the numerator will give you where slope is 0. Right? So slope 0, if you're looking on the graph, then there are places, right, where there's a horizontal tangent line. These are all slope zeros. Okay, next up, if you wanted to find where f prime does not exist, so what does that mean? That means what? Undefined what? Slope. Slope is undefined. And that means a sharp turn. All right. So anything that resembles a sharp turn is the sharp corner of the graph. All right. So these are places, slope undefined, slope undefined, slope undefined. Okay. Then we set the denominator of the derivative equal to 0. I mean, if there is one, right? Not every derivative is going to have a denominator, but if there is a denominator with variables in it, that's where we would look to seek out the place where the graph does not have a slope defined. So in other words, a sharp turn, a sharp point. Okay, so it says to find all the values of that, but in order to do that, we first have to get to the derivative, and we have to explore what rule is required to get to the derivative. Okay, so now let's move towards the calculus portion and trying to get to the derivative function. So let's start off with f of x. How can I rewrite the function so that it's easier for me to work with here? X squared minus 1. Okay, what's the exponent? What power? 2/3, right? 2/3. Okay. Now, we want to find the derivative. Is this something that we can expand? Can I FOIL this out? No, right? That it's got 2/3 is stuck. I'm not able to take the cube root and square root of square the terms of two things that I'm not able to merge. Right? I can't merge that x squared minus 1 into one term. So I'm kind of stuck in this form. I can't clean it up any further. I can't FOIL this out. So because it's stuck in this term, we have to kind of seek out a different way of finding the derivative. And this is where the parentheses is kind of reminding us that there's an outside and inside portion to this problem. And if we can think of this as a composition of two functions, we can apply chain rule to find the derivative. So what's the outside portion of this expression? It's 2/3, okay. What's the inside portion? Okay. So we're going to take turns with each derivative. Okay? We're going to come back to our formula here, f prime of g of x. So take the derivative of the outside function, but rewrite the inside function and insert it into the parentheses. Okay? So let's do that, f prime. Okay, what's outside portion's derivative here? 2/3, parentheses. Good, negative 1/3. Okay, so we took care of this f prime parentheses, and what do we insert inside the parentheses? The original function, right? Don't do anything to it. You're just going to copy it verbatim here. So we took care of this f prime of g of x. I want to keep bringing us back to this rule because I want us to be able to be familiar with what that notation is telling us what to do. What's next? Times g prime times the derivative of the inside function. So times what? Times 2x. Any questions with that? Okay, so there's the derivative. Again, as messy as this derivative looks, it's going to serve the same purpose every time. It's going to describe the steepness of any point on this graph. Okay. But now we're looking for very specific slope behaviors, right? We're looking for slope 0 and slope undefined. So we're going to take these steps there to get there. But let's clean this up a little bit. Let's get this where the numerator and denominator are clearly visible, and let's get it into one fraction so that we can identify the numerator, identify the denominator, and go through these steps. All right. So I want to put the numerators together. What numerator terms can we combine? Or go which, yeah, the 2 and the 2x, right? These are numerator terms. I'll push them together and make it 4x. Okay. Everything's being multiplied and divided, so I can just kind of push things together all into one fraction. And what goes in the denominator? Yeah, 3. What else? 3 1/3, right? Because right now that x squared minus 1 to the negative 1/3 is sitting in the numerator. We typically have an easier time working with problems if we see positive exponents. So I'm going to take that negative exponent, move the parentheses to the other side, which is going to force it into the denominator. Okay, so now we have a clean derivative function. We can't do anything with that denominator anymore, but we can move to the next step. We want to find out where slope is 0. We want to also find out where the slope is undefined. So we're looking for slope 0. So how can I do that? Yep, which is, in this case, 4x, right? So we're going to set 4x equal to 0. Solve for x. X equals what? 0 over 4, which is 0. So we can say that at x equals 0, f prime of x is equal to 0. So we know that at 0, whatever the graph looks like, it's going to somehow show us a slope 0, right? It could be a peak, it could be a valley, right? It could be any of these points, right? Slope zeros, this is wherever the graph is leveling off. Okay. Next up, we also want to find out where slope is undefined. So where do we look for slope undefined or potential sharp points on the graph? Denominator of the derivative equal to 0. Okay. All right, I want to solve for x. A couple of algebraic steps I need to take. How would I start this process to eventually solve for x? Divide by 3, right? We're starting, just wanting to move things away from that x piece by piece. Okay, next up. What can I do to get rid of that 1/3? Raise both sides to what? 1/3. That's going to force that 3 and 1/3 to become 1, which will allow us to just work inside the parentheses there. And x squared minus 1 equals 0. Solve for x. Finally, take the what? Square root. So x equals just 1. Plus or minus 1, right? Anytime you say the square root of both sides of an equation, there's always going to be a plus or minus that shows up. So this tells us that at x equals 1 and at x equals negative 1, slope is undefined. Right? So then what could that look like, right? Like what information do we really find with this? Well, we found where the slope is 0. You can also find out where the slope is undefined. So the graph could look something like this. Right? So slope 0 would look something like this, right? We're able to use the derivative to find a location where that behavior is occurring. We're also able to use the derivative, the denominator, to find out where the slope is undefined, and is able to pinpoint that negative 1 and 1 is where the issue is occurring, where slope is undefined. So I want to continue to kind of give you guys visuals so that it doesn't feel like an abstract exercise, right? That you're finding something that you can visually see and understand. Okay, let's go to the back. Right, so every time we learn a new derivative rule, you're gonna be asked to find the equation table. Right? Same process, find the order pair, find the slope, point slope form. So we could look at this and say, okay, I could go through quotient rule, which is fine. But here's the thing is that if we bring that denominator up to the top, we're gonna have a much easier time relying on just chain rule to get to where we want to be. So anytime I see a constant in the numerator, I'm going to take advantage of that. I'm going to bring my denominator up because that numerator is going to be easy to work with if I don't have to deal with another variable. So let me show you what that looks like. I'll bring the x plus 2 up to the top, which will make it what? The -2. Now, this feels a lot cleaner because I don't have to go through quotient rule anymore. I can just rely on chain rule. Obviously, I cannot distribute that -2 through, but we can clearly see that outside inside showing up for us, right? So let's see if we can go through chain rule here. So let's identify the outside and inside portion. If we can do that, we can always do chain rule. Right, so what's the outside portion? Right, it's the parentheses and everything outside the parentheses. So 4 parentheses to the -2. Okay, what's the inside portion? X plus 2. Okay. So we're going to go through chain rule. Let me write that up here so we can see it. Okay, outside first. F prime. How do I represent the outside derivative? Good. Bring down the -2. We're just pretending like the parentheses is its own variable. We're just doing power rule. Bring the -2 down. It's going to merge with the 4. What's my new exponent? -3. What do I put inside that parentheses? Good, the original function, right? We'll keep reminding us of that. We don't want to jump the gun here. We're not ready for that x plus 2's derivative just yet. Okay? And also, we're just following what the rule says, right? F prime of g of x times, now we can do what? Derivative of x plus 2, which is 1, goes here. Okay. Any questions so far? Are we good? Okay, let's do a little bit of cleanup. Y prime. The -8 stays up top, but I can move the parentheses down because I see that negative exponent. It's just easier to work with positive exponents. Okay, we have our function, we have our derivative. We should be able to start gathering information. Okay, so tangent line equation. What information do I need? Point. So I have the x value. What can I do to find the y value? Original, yep. So 4 over -3 plus 2 squared. Okay, what's my y value? There's 4, right? -1 squared is 1. 4 over 1 is 4. Okay, I have my order pair. Next up, plug -3 into the derivative, right? That'll get me to the slope. -8 over -1. That gives us what? +8. Okay, everything we need is here, right? We have our order pair, we have our slope. We should be able to get our point slope formula. any questions here? Okay, examples 4 and 5, the derivative is a little bit more involved because we got to use quotient rule as part of the chain rule process. And I'll go over that in more detail. Maybe tomorrow if we have time, because tomorrow I do want to spend time reviewing, but maybe we can come back and do these of these more complicated chain rule problems. The homework tonight, the chain rule, I'm not going to check until Monday, okay, but I will send out reminders this weekend for chain rule. All right, don't forget the questions. I'm sorry,
Question.
this is Friday.
Oh, wait.
Friday. It'll be front and back, similar to the morning review, which I'll hand out tomorrow.
Thank you. Fine.